22.3 is like about 20.
You are the only participant.
You asked him about 22.4.
But I have them like complete.
Okay.
I think the only one we're missing is 22.4. We're not really sure how to solve that problem.
Well, interesting.
I don't know, I always get all that.
So 1.1.
Give me 1/2 hour. We didn't cover the topic questions. Let's see something to say.
Hey Sam, come in.
Oh, Dr. Who? Oh my. Oh,
Come on.
I think she's. I don't know if she saw it either. Well, she said she will.
yeah. She's so smooth.
Yeah, the answer is at the back of the book, but it doesn't tell you how to do it.
I gotta get the Lipton after this. I need to burn some energy.
Yeah, that's what he means by it.
Have you ever like boxed before?
I've never boxed.
I want to box. I want to fight Toby. I want to knock Toby out.
That's an interesting problem.
I really hope you try at some point.
I'm gonna like blindside you me in basketball, like just like randomly down the
That's fine.
right to the back.
That's fine.
Guys, just 1 second, okay? The connection seems to have some problem. Okay.
How is Lamar Jackson better than Deshaun Watson already? That doesn't make sense. I'd rather have Deshaun Watson than Lamar Jackson.
I'd rather have Lamar Jackson than Deshaun Watson.
Nope, no chance.
Recency bias is plain false.
You gotta have Deshaun Watson.
Yep.
Really?
You ever seen him throw a ball?
I saw some of Lamar Jackson's throws yesterday.
It does not.
Incredible. You haven't seen it.
That's incredible because like he didn't play yesterday. He played on Sunday.
I'm talking about like on Instagram. You know, you can watch videos over and over and over again. No, you don't know that.
I'm not on Instagram.
Well, it doesn't seem connecting, so I'll step out for a minute to talk to Brad about the connection. I'll be right back.
That's not like a
Right.
great throw.
Are you kidding me? You had to put it in the perfect spot. The perfect spot.
That was impressive. That sidearm's good.
Yeah, it seems not calling today. It's always stuck in the screen.
That's where he is.
Oh, here you are. What did you press?
Sean Watson is too,
Info.
but I think he can.
Okay.
I mean,
So it's already in the call?
You better
Oh, it's on this fast.
Might be the case.
It may have just been left on.
Welcome to a Cisco meeting. You are entering the meeting now.
It may be on the other side. They haven't started.
Only participant.
Yeah, we are the only participants.
What are you talking about up high? That dude almost knocked out of his hand.
Let's hope this is the right meeting room. Yeah, there could be.
Usually in context, maybe something.
Yeah. Okay. Let's see. I'll set up now.
He gets there too.
Is there any feedback? Okay. So then I'll plan to start, but I have recorded class. They can come back to us. If you saw something, just to come into the class and let me know.
Okay, yeah. I will.
Okay. Okay, everyone. Let's get back to the teaching. Looks like today the connection on the ERDC side has some challenge, but it won't stop us to talk about today's lecture. Well, I definitely feeling much better today. Yeah, last Thursday was a little bit rough for me. I don't feel like coughing and teaching at the same time, which wouldn't be fun. So last time we talked about a recapture of what we discussed in the last classes about some basic concepts of stress and strain behavior of material. So we discussed what is true stress, what is engineering stress, and what's strain and what's the draw ratio. We sort of focused on all these topics, and we explained there are going to be some differences between metal deformation versus rubber deformation. So that's going to be the center of the focus today, is teaching about what's the difference between the rubbery material and metal material. I have read the textbook, but I feel like for this particular topic, it's not discussed in a lot of detail. So in the slides we're going to talk about today, we're going to discuss a little bit more detail in terms of differences and mechanism for the metal springs versus polymer and rubber bands, okay? So, and on the top of that, we're going to talk about something a little bit interesting is what's the thermodynamic aspect of two. So we're going to discuss why you can use second law of thermodynamics together with chain conformation we discussed in the first chapter to understand the stress strain behavior of all these rubbery material. Okay?
The students at Vicksburg are available today.
Okay. Got it. So we can continue to talk about today's lecture. So we can think about physical property. So this is very much a conceptual lecture. So let's get started. So what we're going to talk about is the physical state of any material is basically determined by the two factor. And there's two interaction energy. Discuss about all the interaction between different part of molecular versus thermal energy. What's the difference between these two? And why we draw these kind of two very funky cartoon characters there? Because they're always fighting each other and they're trying to figure out what's the competing force between these two. So interaction energy is talking about at the atomic level, what is the force between two components? So imagine you are sitting at an atomic scale. You and your neighbor students will have some sort of interaction force at a, there's many of those type of force could exist. You can form chemical bonds. You can have ionic force, which is electrostatic force. Everybody knows about that. Van der Waals force is something everybody should also learn about this. This is a non-covalent bonds, but it holds all these materials together. Dipole interaction is when your material is, has polarizability. When it's being polarized, you can have the possibility to interact with each other. Okay? And last one, but not least, hydrogen bonding is another very popular ways you can have interaction between different part of molecular. Let me check one thing. It's all good. So when you make polymers, we usually stuck with chemical bond, right? That's how you make the polymers, because along the polymer backbone, you always have covalent bond along your polymer chain. But other forces are very common. In Van der Waals force, that's how you hold the solid material together. So if you think about a piece of plastic, what holds one polymer chain versus the other, there is no covalent bond between them. That's a force actually holding them together. And if you play with a specialized polymer, let's say you play excuse me, polyelectrolytes, then you can have different part of polyelectrolytes have different charge encoded to them. One of the polymer chain can be positive charge, the other negative charge. You have certain interaction force, right? So why we talk about all these? Because all these force is relatively fixed to some extent for a given material, and you sort of have another interaction going to happen in the molecular level is what is thermal energy. Thermal is another way of giving the system a lot of energy. So if your material is at low temperature versus high temperature, it's behave very differently. We can give an example of water. Water has it doesn't have any chemical bonds. It has a lot of hydrogen bonding between different material, between different molecules, as well as the Van der Waals force. But how water behave also very much determined by thermal energy. What I mean by that is different temperature, your water will behave very differently. And everybody knows there's three forms of water people encounter daily. There's vapor in the gas phase, there's liquid phase, and there's solid phase in terms of ice. So what actually we're going to talk about these two is how they actually would help us understand a tiny spring. We're going to talk about how does a spring works in terms of we can understand in using the interaction between intermolecular force. Then we will bridge that with another highly talked about material is elastomer. So in the later half of the class, we're going to discuss for the elastomer what is the contribution. So there's always, from a thermodynamic perspective, there's always two terms we're going to discuss: entropy contribution and enthalpy contribution. So we're going to again start with the enthalpy contribution to understand how your metal spring actually works. Okay? Then we will go to the more specific case about polymer. So this is what we talk about for bulk material. If you think about in the low molecular weight case or in metal, they are the similar system. So let's focus on this very colorful picture, and what it is trying to show is at low temperature your material actually is in the crystalline phase. So by saying crystalline, everybody understands that your material has very regular packing of these atoms. In this case, it shows you have those atoms form phase center, the cubical phase or FCC phase, and they are very regular. This is coming from that you have a lot of attraction force between these atoms. At low temperature, they like to be stay next to each other. Okay? So for small molecules, it's especially true. If you have polymer, you would have regions that is crystalline and some regions are not crystalline. And it's very common for polymeric material, they're all semi-crystalline or even totally amorphous, depends on your material. Like polystyrene is usually fully amorphous. You have PMMA, it can be semi-crystalline, okay? So these materials for small molecule, they will be totally crystalline at low temperature. So if we consider now, there is a large entropy is due to the loss of translation of freedom. What we mean by translation of freedom is how your material can move. As we know in the crystalline states, this particular atom cannot jump to here or there or in the back. It's basically sort of frozen. Okay? So the entropy of the system actually is very low in this particular case. There's only very localized freedom for your atoms to vibrate very close to where its lattice. Okay? And the configuration entropy for a perfect crystal is very low. Or we can claim at 0 degree, it's almost 0 entropy because everything is order. Everything goes to where they want to stay. Now consider a concept of now we heat up the system to a higher degree of temperature. What is going to happen in this crystalline material? We would expect, think about the case like ice. Well, we go up from temperature, it would melt. Okay? Then it would vaporize. So let's consider first case is melt. So when you talk about intermediate temperature, this is what we mean specifically. So the thermal motion will try to increase the entropy of the system. And as the temperature goes up, your entropy goes up, the system will become melt. And you start to generate liquid material. So what's the characteristic between liquid, gas, and solids? So liquid is, you have weak forces holding the molecule still together. In this case, we call it hydrogen bonding. It's holding the water in the liquid phase. But it's not like ordered. There's a lot of mobility in your water molecule, it can move around, right? However, it's not a crystalline either. You don't have a regular structure, your material cannot move. So you would have gains on entropy because now you lose some of the ordering, some degree of disorder, but not totally worst scenario of the ordering, right? And this loss is paid for the loss of some interaction energy. The interaction energy is actually a little bit weaker because we know the density of these two are slightly different. So loss of interaction is regarded the entropy of melting. And we can commonly use a DSC to measure it. And DSC, as everybody should have learned in technique class, I assume? Not yet? Kind of? I expect you guys has learned it in the PCAN, not PCAN, but synthetic lab class. So that should talk about what DSC is. So effectively, you put the two material in a measurement pan and you put a reference pan there and you measure the difference in the heat capacity. And it will go through the TG. I won't steal again. Dr. Nazarenko's sounder. That's called glass transition, which marks your movement of your material. Okay. Then you have crystallization temperature and melting temperature. Okay. You can easily measure all these temperatures. If you put water there, you can tell that's going to be about 100 degrees. If we continue to heat the system up, we would have a high temperature region. A high temperature is characterized by vaporization of your material. What's the characteristic between these two? In the liquid, you still have some sort of force holding all the molecules together. In the vaporized phase, every molecule is very much act as an individual. They can go everywhere they want. A characteristic is the entropy is the highest in this particular case. Okay? So you lose interaction energy, but you gain entropy in this particular case. And this is a very much characteristic of entropy of external degree of freedom. What we mean by degree of freedom, your molecule can move through the large distance and they can have a lot of freedom to them. That's the same saying of the entropy is higher. So this is, excuse me, this is some of the basics or kind of review of the physical chemistry class. How does it relate to our metal spring? What do you think when I squeeze the metal spring happens at a molecular level and why it's want to bounce back? Any guess?
You're pushing the metal particles closer together, and that's going to, at this temperature, going to be unfavorable, so it's going to spin backwards and increase the entropy term.
That's a very good guess. So that's pretty much related to what is the molecular level of force. And I'll just talk about a little bit more in the next slides or two. So for the metal spring, what the key characteristic when we squeeze them is we don't squeeze them in a straight direction, right? It's actually engineered to be a coil. And when we deform the coil in the vertical direction, we delocalize all these strings slightly in the horizontal direction. So you have a little bit of shear force between each metal, and they would like to reflect back once the force is released. That's related to the intermolecular force. So we're gonna, before we talk about that, we're gonna talk 2 more things about some fundamental concepts about free volume and the glass transition. So free volume is a concept has been widely used in explaining the glass transition phenomena. So free volume is conceptually some sort of free space I can move around near me. So even you consider a plastic bottle, it's packed very solid, where we are seeing now, but at a molecular level, it's pretty much sitting like you guys sitting in each of chair. There's always some room you can move around you. And that's characterized by free volume. It's a theory has been actually empirically used for many decades. Sonia, you have a question?
Do more rigid systems then have less free volume?
So does rigid system has more free volume? It's not directly related. So free volume is more related to discuss about TG. And TG has some influence about mechanical property of a material, but it's not all about it. There's other factors come into play. So what we want to say is, in the low molecular weight system, or oligomer, or small molecular, at high and low temperature, the difference is considering the free volume. So when you cool water from high temperature, the free volume is highest at very high temperature. It will pass the crystallization temperature about 0 degrees C first, and then it will also pass glass transition temperature if you have a polymeric material. Okay, so let's see example of polystyrene. So every day you use polystyrene. What would you think about the serviceable temperature for it, for structural material? It works perfectly at room temperature, but not at high temperature. If you put a plastics, even closer sometimes case, your hair dryer, if you blow it, or heater, it will soften and it can bend. Well, in some cases, I saw handymen trying to join a connector with a tube, PVC tube. What they do is basically heat it around, use a heater gun, let it soften, then connect them, then put some metal clamp to fix them there, right? So that's all about glass transition temperature. So in the free volume, if you think about crystallization, then that's what happens is at high and low temperature, you have different free volume. At high temperature, you have much higher free volume. At low temperature, you basically, the thermal force is not as strong as attraction force. So you will have reduced thermal volume, okay? And a lot of example I show here. This is a show as two material. On the left, it's silicon dioxide. On the right, it's also silicon dioxide. But how they packed it atomically gives a totally property. So if they're perfect crystalline, it's typically quartz glass, and they have much better mechanical property. On the right hand, if you have totally amorphous silicon dioxide, this is we know as glass, like on every window. It's not a regular packed, but it's also don't have the mobility to move at room temperature. So we usually call them just glass. Okay? So a little bit backgrounds about free volume and motion of molecule. So when you start to have polymers that connect with each other, the story changes. Although the behavior of it is pretty much governed by the same factor, you will still have the attraction force between different parts of molecular, but now connectivity plays again the role. If you guys remember what we talked about, similarly as Flory-Hagen theory, when we talk about connectivity versus solvent system, where we now have the lattice theory versus Flory-Hagen theory, right? So in here, similarly, if you look at here, so when you now deform polymer chain, the polymer does not move a single unit. The free volume of the free volume in the system is not big enough to hosting the movement of your whole polymer chain. So it needs to be considered as differently. So move of the segment is typically accompanied by rotation around the backbone. So there's a lot of famous theories along these lines. One of the very famous theory for the polymer you're going to study next classes, next years, is about repetition theory. So in the melt states, how does polymer move around each other? It doesn't move as a chain can pass each other, but it's move around the tube, measuring tube. Here it's polymer backbone. So all these will tell us it's very different for the polymer that need to be moving around or have the free volume. Okay? And in terms of last point, polymers are very likely to form glassy phase, because the polymer, as you can see, when it needs to crystallize, it does not only require a part of your polymer to move, but also the connected part. So one part of polymer chain needs to move into the crystallization side, then consecutively the rest of part of the chain needs to float back and forth. Compared to think about salts or metal, when they crystallize, they only need a single ions or element to move into crystallization side. So degree of crystallinity is much lower for polymeric material, very commonly, okay? And you don't have 100% crystalline material. Like polyethylene is well known, and you usually have crystalline percentage between 30 to 70%, depending how you process them. But it's not possible to have a 100% crystalline domain. Compared to the other material, like small molecular, you can grow single crystal. That means it's 100% of crystalline domain. Everybody has a general chemistry class in your college. Have everyone grow any single crystal in the lab? It's quite an interesting process, right? Usually, like example would be you have a sodium chloride, you dissolve them, and you keep adding them until they form non-soluble. Then you heat up so that it's oversaturated at that concentration. But because the temperature promotes solubility, you can have an oversaturated solution. Then you slowly cool down, you can start to have them precipitate out and crystallize. And these are ways you can grow 100% of crystalline inorganic material or small molecular, okay? But polymers, they can, because when we talk about free volume they only have little room to move around. And it's very hard to have 100% crystalline material. There's always going to sound imperfect there. So let me first discuss this part first. So now come back to how do we discuss the deformation of the metal, okay? So we want to come back to this energy diagram as shown here. So let me highlight this particular energy diagram. So it's very generic energy diagram, shows how does the energy of the system of two atoms, you can imagine, changes versus different distance between atom separation. So you can think about, this would be a metal atom like iron, in this case, in one of my hand, in other of my hand. In the crystalline domain, they would fit in very happily in this bond length, which is show R0, or this distance, and this would represent a crystalline domain of the iron, okay? And it's pretty happily there. And what if we deform these lattices? If we squeeze them or pull them apart, and their characteristic energy diagram is shown in the above. You would go through two different regions. So on the top, or the red, it represents there's a repulsive force, which means they don't like to be that close, okay? And on the other side, you would also have attraction force, which means if they are a little bit away from each other, they like to be attracted. And in the most ideal case, our system is always sitting in the bottom of this bond length. And this type of work can be described in a little bit more detail as we're going to discuss. But what we're trying to say here is, if you look at the system, because of crystalline structure, as we mentioned in this particular iron, the entropy contribution is very low. The entropy contribution during before and after deformation is not changing that much, right? So before it's crystalline domain, so we know entropy is close to zero, if not non-existent. After small deformation, you have a distance between intermolecular distance start to increase up, but it's also not that disordered state. It's not a gas phase as we stretch it, right? We also don't stretch your crystalline material into liquid-like material. So entropy doesn't change. So it's purely enthalpic nature. There's changes in the enthalpic energy while we deform it. Okay? And we're going to explain to you what is enthalpic in this particular case. So we want to go very much deep in the knowledge about the mass, but we're going to show some simple equations here. So near the equilibrium point, we can sort of summarize the potential energy to be potential energy U would equal to C as a constant equals to R divided by R0 squared. What does this function will give you between U and R? It's a parabolic shape of the curve, right? Because it depends on R minus R0 squared. It pretty much represents, if I cover all the top and you only see the bottom of the energy diagram, that's basically the parabolic shape of your energy you're going to have. And what that energy diagram says is, if you deviate from R0, you're going to increase your potential energy. kind of makes sense. When you deviate an atom from the lattice preferences space, they're going to either repulse or attract and trying to go back. So, in the first law of thermodynamic, we have du equals to dq. Q means the thermal energy changes in the deformation. We don't think there's much. And dw. W means the work you did into the system. And how do we define the work is basically related to a function. We won't talk in more detail, but it's basically F, the force, or spring constant for the material will be equal to potential energy, first derivative in terms of R. If you take first the derivative with respect to R, that's what you get, will be 2C R minus R0. So what's the spring constant? It tells you that you have you have now a formulation you can calculate what's the force would be happening to your spring if you know what is the C. C is basically a constant, depends on your material's property. So you can also calculate stress will be equals to the force divided by area, and you can get the elastic modulus based on this particular material system. As you see, the elastic modulus is not linear, particularly. It depends on what is this stress will depends on this E and the strain. And you can calculate out what is the strain using this particular equation, so you can understand what's the elastic modulus E for a particular metal piece. And the only reason people develop this to be a coil shape is this assumption is you only have small deformation in your material. Okay? If you deform it largely, it will not come back or move back to what is original shape. So if we make a stainless steel rods, just a rod, is it a spring? It is, but it's only on the tiny little deformation scale. If you deform it outside, let's say 0.05%, it's no longer elastic. And because the modulus is so high that it's also not useful for some of the force, you only requires low bending modulus, okay? So very smart engineers develop these coil shape, and they're pretty elastic. You can do compression or tensile. They would behave very much similarly at the low degree of strain. Because what at the molecular level, if I have tiny, I have a super magnifier, I can look at the atomic scale. Let me go back one slide. If I do any work to this particular spring, what happens is always changing the distance between these two atoms in a lattice. When I compress, these get closer. When tensile, these two atoms get a little bit further away. And because of energy potential in the intermolecular, interatom forces, it's always trying to come back. So how about polymer? What would you guys think would be different? A rubber band? Well, stretch it. You also feel the elastic force. But see the differences? It does not require me to make them into a coiled shape and start to compress in this way. And I can deform this very largely. You know, hopefully this doesn't burst, but I can probably like 500, 400% until I can feel there's a limited, deformation degree I can get, right? But in the first region, it's very easy to deform. Very different with this one, okay? So we're gonna take a short break, and when we come back, we're now gonna start moving from a metal spring, which we explained through the enthalpic interaction between the atoms in the molecular, to what's going on here, okay? we can take a 5 minutes break.
I left a couple minutes early, clearly.
Hmm?
Said I left just a couple minutes early.
Yeah.
Yeah. Do some jumping jacks.
Okay, let's resume the second part. So this part, we're now going to discuss about the how to understand the deformation for particularly rubber material and how does it differentiate with a metal spring, okay? Before we start the class, we need to talk about one thing. In particular is we need to understand a little bit of thermodynamics. And this can be a bit challenging to explain very lively, just because it's a very abstract concept. But I'll give you a big picture why we need to do this. So let me give you introduction about what dominates in terms of these forces happens at rubber bands. Anyone want to give some thoughts about what potentially would be the mechanism for the rubber band to deform and restore its original shape versus metal spring. I'll give you guys a hint. We are a polymer science department, so it's definitely related to polymeric nature of a polymer chain. So if you can zoom in again, at the molecular level, what do you think happens when I stretch this to like 3 times in a rubber band? Do you guys think what happens is, because molecules between polymer chain A and chain B is being attractive, and we separate them, they want to come back? How many of you think that might be the case? Sean? No? Everybody is just scratching hand or raising their hand? It's probably not the case, right? Otherwise we won't discuss it. So what's a possible reason happens at a rubber band?
Chain entanglement, chains become less entangled. Or
Chain entanglement.
chains straighten out.
Let me tell you, chain entanglement is related to this process. But we will talk a little bit later in the next class how entanglement would affect rubber band's property. What I can tell you is entanglement, or we call it cross-link density, affect how rigid your rubber band is. Okay? So if you have more cross-links, more entanglement, your rubber band will be hard to pull apart. Any more thoughts? Covalent bonding? But when we pull it, we don't break the covalent. Covalent bond is very rigid. You cannot deform a carbon-carbon bond from 1.5 angstrom to, let's say, 4.5 angstrom and expect to retract back. Sonia?
The Vander Waals interactions?
Vander Waals is part of the, it's very prevail in the solid states property, but not the case here. It's not responsible for the elastic property, but very much responsible for mechanical property overall for other amorphous material, like polystyrene. Why it's rigid is related to the Vander Waals force, or the generally what's the force holding a polymer chain versus another polymer chain together, okay? But not responsible for elastic property.
Change how much the chains are coiled.
Yeah, entropy and how much the chain is coiled is exactly the case here. So entropy is a real reason, and I sort of want to talk about this first because this helps you guys to understand what's the difference. There's not a lot of enthalpic differences, but think about entropy. What happens is, before we stretch a polymer rubber band, at a molecular scale, you have sort of polymer chain adopting a Gaussian coil. And when we pull it, you elongate at a molecular scale picture, we elongate individual polymer chain, assuming these chains are sort of adopt a fine model. What that means is those chains would be follow the deformation macroscopically. At the atomic level, if you think about when first lecture we talk about is Gaussian coil. When we pull this rubber band 3 times the length, that means we also deform the Gaussian coil to be elongated Gaussian coil. If somehow we are, again, I want to use the case of Ant-Man, if 2 of them, one pulls the chain head, one pulls the chain tail, you can definitely deform it. And that's the case what happens in the rubber band. In the stretched case, how does the entropy compare towards its beginning? Increase or decrease after we stretch? Increase or decrease? I heard mixed. How many of you think it's? How many of you think it decreases? Half of the class? A little bit more than half? So the rest of them, I think you think it's increases. But entropy, remember, it's related to the states of configuration. You can think about the case when if your chain is fully relaxed, there's more ways you can adopt the Gaussian coil. When it's elongated, you have less possibility to adopt its elongated state, okay? So effectively, we lower the entropy. And we know this is not the preferred for the nature. It does not like the system entropy to go down. It's always spontaneous want the entropy to go up. So that's why when we release the force applied to rubber bands, it's actually go up spontaneously, because the chain is very happy to relax back to its coil states. It refuses to stay at elongated states. It sort of captures the essence of the difference between these two. Now you can see this is a enthalpy driven process. It's basically we are tuning the inter-atom distance to affecting it. Well, this one, we are effectively changing the coil shape of your polymer chain, and it's affecting the elasticity or entropy of your material. So can we do better than that? It's just a conceptual explanation, but can we go a little bit deeper to explain the theory about rubber elasticity? So this has been a fascinating problem for the polymer physicist. So there's quite a lot of people working on this problem to explain how to understand the elasticity and the modulus of the rubber. And specifically, we're going to introduce two models for the class. The first model is just going to be very generic, using the entropic case to understand the rubber elasticity. We make a lot of simplification. For example, I will speak two very simplified cases. When we discuss the idealized model, we assume there's no enthalpy change while you deform it. But that's not always true. There's always a little bit enthalpy change even you deform a solid film, okay? But it's not as big a contribution as the other. And second is we assume you have a very much uniform network and it's affine to the deformation macroscopically. So we call it a affine model. But in reality, because of the density of cross-link changes between different parts, so you wouldn't be able to meet all these assumptions. And in the next two lectures, we will talk about what can be assumed and what cannot be assumed. However, the theory is so successful, it can predict what's the modulus of your rubber based on the entanglement density, and we will learn about that. As you can see, the more degree of cross-links, it's getting more rigid, right? So we're going to learn all these. And second way where the theory is very successful is predicting the nonlinear behavior of the rubber band. So let me show another example. I'm going to pick so for the spring, what we have is the force. Let's say L is displacement. It's pretty much linear for the spring right here. But for the rubber band, if we plot jaw ratio and the force, it's actually not particularly very linear. You would see a substantial increase in terms of force in the later stage of deformation, and there's a little bit plateau in the middle, and all these can be explained from the rubber elasticity theory. Okay, so we're gonna use the next few minutes to set up some frameworks how we can understand this. So now question back to you guys. It's a very generic question. How can we link what we learned in the first months of the lecture in terms of chain conformation and second class of Flory-Hagen theory to what we're going to do for rubber elasticity? I'll give you guys a hint. Thermodynamics. We basically assume that the rubber elasticity all comes from the thermodynamics of the entropy change, right? We know from the second lecture what would be the entropy change for different possible state of configuration. Everybody remember that? We calculate the entropy for a lattice theory, and we understand how does the entropy changes with different ways you place all these molecules. So the same argument can be applied for these Gaussian coil. So you have a coil is in the fully Gaussian state, how many possible states can be adopted, and how many after you stretch them can adopt. So this can be applied, and you can use what we learned from chain conformation and what we learned for the entropy related to possible configuration of state. We can calculate what's the entropy change before and after you're stretching the Gaussian coil, right? I'm just speaking about the broad picture what can be done. What else can be done is we can relate the entropy using the first law of the thermodynamics to the force we apply to the system. What you apply to the system, if we assume there is no enthalpy change, all the forces, entropy differences contributed to the changes of the work done onto your material system. And we know how much displacement of your polymer after we stretch it. We should be able to calculate out how much forces is being applied to your material, right? And listen carefully this one more time. This is very critical for the next class. If we know what the entropy change in the system, when we pull your rubber band, we can calculate entropy at 0 state, at this state, right? Then, if we know the displacement, if we assume there is no change in the thermal enthalpy in the system, we can calculate how much work being done in the system, because it's a closed system. All the entropy is basically changes is basically coming from the force we apply. If we understand that, then we can explain a little more carefully in the first law of thermodynamics. It's very typical physical chemistry class you would learn in the college. So internal energy of the system, U. What the internal energy means is just all the energy available in the system can be changed either by adding heat or work. Okay? So adding heat means you heat up the system. Work means if you think about engine for your truck or for your car, if you don't work to the system, means you apply a force, you can change the internal energy, right? More specifically, classically internal energy of the system is given by pressure multiplied by changes in the volume, and it's a minus sign. So PdV is typically given the work done. Think about a very classic gas engine. The work is basically on how much pressure you have in the engine and how much expansion of the volume you done. That's called the work. But in our material system, we need to consider the force down at the distance, because we're not changing the volume and changing the pressure. We basically have the constant pressure. But what we have is a force pulled your rubber band for a certain distance. This gives you the work down FDL. Force multiplied by distance going to be the work. First law of thermodynamics. All right, now we jumped into second law. I may should ask you guys what's the third law for the quiz. Just for the completion, right? So everybody knows second law of thermodynamics basically tells you the Gibbs free energy would be equals to enthalpy and entropy change in the system, right? And we know the delta H is very much related to the internal energy, so we can rewrite the equation above just use internal energy, U, work done at the system, PV, or TDS. And we also know the du, based on the equation above, can be rewrite into this particular equation. Any question for this part? It's a little bit abstract to understand all these terms, but you want to categorize them into the work done in the system and the entropy of the system, okay? Entropy is always S multiplied by T. Mark.
Earlier it says that no volume change occurs, so do we need that middle term even?
No. We will come into the next slides, we will explain a little bit more detail. So now, if we rewrite it a little bit, we can rewrite delta G will be equals to delta G, take a partial derivative to the pressure at a constant temperature and the distance L, plus second term. This is basically S definition. S can be rewrite as delta G multiplied by T, divide partial derivative of temperature at a constant pressure in L, plus the last term. Last term is basically says delta G would be equals to F dL. F would be equals to partial derivative of G at distance at a constant pressure and temperature. Because if we assume at constant pressure or temperature, all the other term is basically negligible. It's not going to change, right? So the whole purpose of this, what we're doing here is link what would be the force of your system, and depends on delta L and delta H and delta S. So the force basically is equivalent to enthalpy change, partial derivative of distance, and entropy change, partial derivative of L, both at constant pressure and temperature. And this we can satisfy. As you can see, when I pull a rubber band, I don't change much pressure or temperature for this rubber band. Okay? This is a very important equation because this helps us to the later on understand how can we derive theoretically what's the mechanical property for a rubber band. I'll give you a hint. As I mentioned, we don't worry too much about enthalpy change for the formation of the rubber band, although there's are changes, don't get me wrong, but it's negligible compared to the enthalpy change in the material system. Because when we deform a rubber band, we still deform slightly the distance between one polymer chain to the other. The distance change, if you recall in the last chapter, the distance change between one polymer chain to the other, we define a parameter if we pull one chain totally away from each other. That's called cohesive energy, right? They are not zero. So this is non-zero, but is negligible. So assume we can remove this term, then we can build some theoretical work about how does the force of your rubber band depends on partial derivative of entropy by distance of the poling. Temperature is always going to be a constant factor here. This is a little bit abstract, but think about logic flow, how we get there. We take advantage of first and second law of thermodynamics. We link to how does the force, the work done to the system, to the entropy change to the system. So effectively now we can measure how much force is exerted on a single rubber, a single chain inside of rubber bands, and understand how does it depends on entropy change. And do we know the entropy change for the rubber band before and after poling? Do we know it? We can't get it, right? We know that it's gonna, after we pull it, it will decrease. And as long as we know how many possible ways your chain can configure, we can use a very classic equation we did in the last class. S would be K. This is possible states of your configuration. We can calculate out what the S is, right? So if we know the initial state and end state, we can effectively understand all the mechanical property for a rubber band before and after deformation, because all the information is there, but we just need to be a little bit brave and understand the mass behind it. We won't have time to go through all the math, but that's the focus for the next class, is we're gonna take advantage of this equation. We assume there is no enthalpy change while we deform the rubber band, and how can we use the entropy change to define the rubber elasticity theory? That's gonna be fascinating, because we basically can predict, if you know the cross-link density, what's the modulus for a rubber band. And it works greatly. Let's say, as I mentioned the modulus to you guys a couple times for the rubber band, this is on the megapascal level. And typical cross-link density between a polymer, what I specifically mean, or maybe it's easier for you guys to understand, is a typical rubber material has long polymer chain. The molecular weight is typically on hundreds of kilodalton, very high molecular weight. There's multiple cross-link points going to happen along this single chain. All right? And for each two cross-link points, if you measure the molecular weight between, that's we call the molecular weight for these cross-linked segments. Okay? They're surprising. They're typically on the order of a couple thousand kilodalton. So for a long chain, you have tens of hundreds of cross-link points along it. And this, a few kilodalton, you can use the rubber elasticity theory to predict their modulus will be on the order of megapascal. If you cross-link them 10 times lower density, which means instead of putting so much cross-link points along the backbone, the modulus will drop proportionally. In other words, using the rubber elasticity theory, we can understand how does modulus change versus different degree of cross-link. We will talk more in detail, but I hope this lecture is basically trying to come across an important message. Why our polymer, wait, where's my spring? This looks like it's dropped somewhere. Did it drop here? I need to take it back because I took it from the pen. So it's very different between a spring, a metal made, versus a rubber band. And I want to mention this one more time. One is enthalpy dominant. It's all about intermolecular forces, and when we deform it, how it changes with interatom distance. And this is very much entropy dominant. And all the work down to your rubber band is related to change of entropy of your polymer chain. Again, if you recall the Flory-Huggins, the entropy comes into play again. That's very characteristic about polymeric material. And in the next lecture, we're going to go more details to explain how we can predict the modulus for a rubber band simply based on the rubber elasticity theory and second thermodynamic law. Okay? So you guys feel free to read the textbook about chapter 10.4 and 10.5, and those are related to the lecture we're going to talk about. Okay? All right?